and restart the recording so that I don't have to re-give this lecture to my basement tomorrow. I gotta tell you, it's a lot more fun talking to people than talking to myself. All right, so this is like a catch-all because models for other kinds of not normal, right? Here's a list of choices that you can have, including something that's not considered a generalized model called quantile regression, but which I think is super useful, and I want more people to know about it. I didn't know about it until I was an associate professor. So it's never too late to learn. That's the thing. You'll never have as much time to learn as you do right now, but to stay like fresh in your field, lifelong learning is what we got to commit to. So I found that later in life, but I think it's super cool. So I want you guys to hear about it. So other kinds of not normal outcomes, wrapping up this type of thing here. So here's my list of where we've been and where we're going. So the class, generalized linear models, where ized means some kind of not normal. And the way that we predict something not normal is by adding a link function to make sure that its predictions stay within the boundaries of the possible outcome, and by changing out the conditional distribution to something that's better suited for whatever its possible values are as well. So we did categorical, in which the link function was either logit or probit, or log-log or complementary log-log for things that were skewed, where there's way more zeros or ones or vice versa. And in that case, the distributions were not a question. Let's put it that way. If it's binary, then it's Bernoulli, the end. If it is ordinal or nominal, it's multinomial, the end. Like you can't be wrong with respect to that, other than ignoring nesting. Counts is what we just finished. So in that case, the link is going to be log, pretty much no matter what. Then the question is, what kind of distribution do you need? For regular counts, Poisson or negative binomial are the go-tos. For zero inflated, you might want to add zero inflated submodels or hurdle variants to address the extra zeros in those, and then we have decisions to make as to which distribution is going to work relatively best. Where we are at now is proportions and truncated stuff and skewed stuff. So these are continuous outcomes, but that still have one or more boundaries to them, and which makes them not normal. Okay, so normal. In addition to just being the shape, a big thing about using the normal distribution is that it does not have boundaries. Like theoretically, you could predict anything from negative infinity to positive infinity using a normal distribution. It just gets less and less probable as you move out into the tails. But in real life, I can't think of any outcome that doesn't have a boundary of some kind. Like in my brain, I can't think of anything. Even scale scores, right, that may have, a huge range to them, have a ceiling and a floor, right? The GRE stops at what, 100? 120? Anyone know? I don't know. I'm so old that my GRE had a mean of 500. My GRE went from 300 to 800. That's what I know. Maybe, I feel like it's 100. Point being, every scale has a ceiling or a floor. There's some kind of boundary, even for things that are continuous. So these types of outcomes would include things like proportions or rates, like percent correct is continuous. It can have as many decimal places as you have items to fill them out, but you're stopping between 0 things right and all the things right. Scale scores, and in these types of things, if it has two boundaries, so it has both the ceiling and a floor that the predicted outcomes have to stay within, then we can use some kind of link like a logit or probit, but then we're not sure what kind of distribution to use. That's going to be an empirical question. There's also outcomes that are continue-ish, is the term that I'm inventing for this, that are bounded only in one direction. Yeah, continue-ish is not a real thing, by the way. That's just my word. Because it's like continuous treated as, but it's not really. Things like response time, right? There's some minimum level of response time by which the human body can't go faster. I think it's maybe 200 milliseconds or something like that. Salaries, right? You can't have a salary that's less than 0. And you're like, yes, I can. I'm a graduate student. I'm incurring debt as I'm sitting here. But once you have a job, right, you can't make, negative $10 a month or something. Now, after you pay your bills, that is entirely possible, but that is a different quantity. Minutes of physical activity a day. The lowest you can do is nothing. You can't have negative 10 minutes of activity. So these outcomes then have a different solution to them. In most cases, we're going to do a log type link, because they're bounded at the bottom but not the top, same as counts. But then the distribution that we need to go with it is something that's continuous rather than discrete, because you can have non-integer values as well. So logit links are used in predicting proportions. To do this, though, it requires a little bit of rearrangement in your head. So you're used to thinking about logits for binary, right? 0 versus 1. So let's say that I'm predicting one item and you can either get it right or wrong, right? Logit for that. Now, what if I'm predicting 10 items? I can think about predicting the proportion correct across 10 items in the same way by saying that any one item, I can still use a logit to predict whether it's a 0 or a 1. So in these models, what ends up happening is we're going to use a logit to predict the probability of getting any item right across a series of multiple items. And we can take that probability of getting any item right, multiply it by the number of items, and that gives us the expected mean. So I think of this as directly predicting proportion correct, even though what we feed into it is actually going to be number correct and the total possible. So there's like an extra data manipulation step that it takes to do this. So when predicting the outcome, the logit of the probability, any one trial, that's what we're predicting, it gets multiplied by the number of trials. So I'm using trials and items as synonyms here because I was just teaching SEM, a half hour ago where we're talking about items. It becomes the predicted number of ones mu. So there is what you're going to get in your output is still the probability, and it's going to be proportion correct. Like that's what it's going to be. It's just the way that you get there is a little bit indirect and convoluted. I will say that any outcome that has ceilings and floors, even if it's not between 0 and 1, can be converted into a proportion type outcome with this formula. So if you have a scale score that ranges from 10 to 50, you can still use a logit for it. You just have to transform each of the values into being like the proportion out of 50 that you have, like between 10 and 50. So it'd be like from 10 to 50. So in terms of the model is going to predict logits, the same as before. And then we can convert that probability back from logits back to probability. So it's the same link and inverse link as we had for binary and categorical. That means we're back to odds ratios as units of effect size. So e to the slope gives us the odds ratio, where negative slopes go from 0 to 1. A 0 slope is an odds ratio of 0, and a positive slope goes from 1 to positive infinity. The question then is what kind of distribution? So in the same way that Poisson is usually not good enough for counts because it says the mean and the variance are supposed to be the same, you can use binomial. And it has one parameter. It has p as the parameter. It doesn't have an estimated variance. So in proportion correct type outcomes, we have to worry about over dispersion the same way we do in counts. So your choices then, there are sort of 3 different kinds that I'll walk you through. Binomial, which is like the standard one, that predicts only one hump, so to speak, so like the distribution is skewed. I'll show you a picture in 1 second here, and it includes zeros and ones. So that's nice and flexible because it could be the case that some people got nothing right and some people got everything right. Beta is way more flexible in that it can handle bimodal distributions, or even probably trimodal. It can do about anything, but I will never ever be able to understand the parameters of it, like ever in my life. And it doesn't have zeros or ones. So functionally speaking, beta is not that useful. But we can sort of meld the two into something that is called beta binomial, which is analogous to negative binomial in that it allows over dispersion in a binomial. So that's what's going to work best, I think, a lot of the time. And here are the routines in which you can find these things. So I have an example from, again, my previous work showing you how to fit these models. So here's what binomial would look like all by itself. It has the probability of your answer being however many number of trials that you got right is the total number divided by that with factorial sign here. So that's not an exclamation point, that's factorial. And it works to create a distribution that looks like this, where the mean is the probability of getting any one trial correct times the number of trials, and then the variance is a function of those things too. So it's the same idea as binary, where the variance is the mean times 1 minus the mean, just with the number of trials put in here to get it up to the total that's possible. So the blue distribution here has a probability of 0.1 as the mean, and so it's expected to look like this. So note that it understands that the lowest that you can be is 0% correct in terms of these 20 trials. Red is symmetric because it has a probability of 0.5. And so for something like this, a normal distribution may not be too unreasonable. And then green would be like if there's a ceiling effect, excuse me. Coughing fits. I would say I'm throwing that in there just so you believe me that I wasn't playing hooky on Tuesday, that I'm actually sick, but this is no fun. I have like mucus coating my vocal cords and I can only use them for like 10 minutes before I start hacking, but I know. Yeah, poor me. But I get to teach on Zoom and then I don't have to cough all over you and make you sick. So I think that's a win-win. Anywho, green is probability of 0.9. So it understands then that you can't go past 20 items correct. So binomial is really built for this situation of like percent correct or accuracy rate as an outcome. It's just that it doesn't expect much skewness. So like if you look at the blue here, it doesn't expect anyone to get more than 6 items right if the probability of getting any one of these right is only 0.1. And the converse is true for green. It doesn't expect anybody to get fewer than like, let's say 13 right if the probability of getting each one right is 0.9. But this may not be reality, especially if you're dealing with multiple populations. Like if you're giving a test on like some kind of algorithmic skill, right? Like my son is working on division right now. Like either you understand it or you don't, then there may be like a subpopulation of stragglers down here that drags this curve like all the way back down over to 0, right? There may be kids who get none of this right, even though on average 90% is correct for each one. So that's where like the skewness, you need something to allow that additional part of the distribution to exist. And that's where binomial by itself is not going to do that. It's not designed for that situation. And we'll try to add some stuff to it that works. So over dispersion, that's the vocabulary word. And our diagnosis for it is going to be the same as for counts. We have this statistic called Pearson chi-square over degrees of freedom, which gives you essentially like the variance in the data for real relative to what the variance should be as assigned by the model. And the best case scenario is that data matches predicted model, and so the ratio should be 1. To the extent that the ratio is greater than 1, you have more variance in your data than what the model is anticipating. That means all of your standard errors are going to be too small, your p-values are going to be too optimistic. So this can be caused by a number of things. It can be caused by having an incomplete model in terms of what predicts the probability in the first place, skewness or nesting or clustering. So this overdispersion can be tricky to solve. I'm dealing with a situation in which we know that there's no nesting or clustering, for sure. Like you should know that in your sample to begin with before you would pick this type of model anyway. And by the way, if you have nesting or clustering, do you know those terms, what those mean? The idea that some people in your data set are more related because they belong to something in common, like the same family or the same school or something. Do you know how you fix that? You come to my other classes is how you fix that. So this fall I'm teaching longitudinal analysis, which is for repeated observations from the same person over time. And last fall we did clustered multi-level models, probably coming back in about 2 years. So that's how you fix that, is you come to those classes instead. Once you know all of this stuff, though, adding the multi-level component will be much more straightforward than if you're trying to add everything new at the same time. So there's 2 ways of adding extra variance into this distribution so that you can allow for essentially skewness coming off of where the curve is. One is known as additive and the other is multiplicative. Additive has a special name that I found in the literature called observation level random effect. And for those of you who do know multi-level, we're going to add a random intercept in, even though this is single level data. Like, what? You can do that? Yes, you can do that. And that's how you can add in additional variability. Multiplicative, though, I think is a better option because it's unusual that you would just have additive variance. It should increase as a function of the mean, which means that it needs to decrease as you get closer to the zeros and the ones. So it should have the same type of spread that you would see in binary data. So we'll be doing both of those in example 4 as well. So here's what beta looks like, by the way. I stole this picture out of Wikipedia as per my usual. And these are two different parameters known as shape, both of them, alpha and beta. And these are different predictions for what you would look like if these were the different values. And I can't really make heads or tails of this. Anyone here more familiar with beta than me? No? Yeah, I don't know. Like, if they're both 0.5, then you get this sort of bimodal thing. If they're both 2, then it looks sort of normal. Like, I don't know what to do with this information, to be honest. I know that this is how you find the mean and the scale and the variance, but beta itself is not a plausible distribution for most real cases because it doesn't include 0 or 1 values. So you'd have to kick out people who got it all right or all wrong, which is dissatisfying and not helpful. Alternatively, you could add 0 or 1 inflation. So the same idea as the structural versus expected zeros, like the hurdle thing, it's back. You would essentially add a submodel for are you a 0 or are you part of the beta distribution? And if you had a 1, you could add another submodel, so 3. Are you a 0? Are you in the beta distribution or are you a 1? Good luck explaining that to anyone. That's also not helpful. So we're going to do sort of a hybrid approach. Beta binomial includes zeros and ones. It doesn't have multiple submodels, but what it does have is an additional sort of scale stretchy factor, the same way that we had a negative binomial that allows the variance to exceed what it would supposed to be in the regular binomial. So I found this. It seems very useful. The only catch is that figuring out what you get in your output is very tricky. So I wrote this down so I wouldn't forget. So we get a scale factor directly out of SAS. We get 1 over that in Stata, and we get the log of 1 over that in R. Yes, and those faces like, what? Yeah, I know. I know. I didn't make this up. I'm just the messenger. So either way, though, you can do some kind of likelihood ratio test that tells you if you need this thing in the first place. And then if you do, you can figure out which permutation you have based on that. But it's the same idea, though, as counts. It's like you have this sort of standard distribution that predicts some kind of relation between mean and variance, and to the extent that you have extra skewness, you need to add more variance in with the scaling factor. That's the big picture. All right, so extra zeros then. Same issue in terms of counts. So you can have too many zeros in these distributions. You can also have too many ones. Usually not at the same time, but either way. So if you have extra zeros, then you could have, excuse me, this type of zero inflated model where you have the first model is predicting all of the probability in terms of the probability of any one trial being correct, which would include the entire thing, and then the probability being an extra zero. This is just as confusing and weird as it is in the other one, but it allows you to test whether you have any extra zero inflation. Unfortunately, hurdle versions of this I have not found. So the issue in terms of hurdle is that you would have to find a binomial distribution that doesn't have zeros in it for this to work, for you to move the zeros into a different submodel, and I don't know of one. I looked, I couldn't find one. So it doesn't mean they don't exist, it just means that I can't find it. So for this family, I don't think hurdle type things are going to be as useful as zero inflated type things, in which case we have an extra submodel, but I'll give you an example of how that would work. Okay, yeah, that's the end of that section. Okay, so we're ready to look at an example. How's that sound? Examples are always better, aren't they? And I didn't even think we'd get to it today, and so I didn't even open it. How about that? This is like the first time ever I've gotten further than I thought I would. So this is a true story. Okay, I want to show you the picture first. Here's the outcome we're predicting. How would you describe this outcome? This is percent correct on a test of grammatical understanding in third graders. If you were in intro stat class, what vocabulary words would you use to describe this?
Left skewed.
Yeah, left skewed, or is it negative or positively skewed? Yeah, this is like, which way does it go? Yeah, negative. It's where the tail is. That's how you remember. It's backwards from how you would think about it. Yeah, negatively skewed like big time. The reason for that is because this is actually the last occasion of a longitudinal study in which children are acquiring the ability that this test measures. And so by the time they get to third grade, they should be pretty good at it. Just ask my third grader. He's great at everything. Children have no problem with self-concept, I tell you. So in my publication here, and I say it's mine because look, I'm third author, that's me. This is something I worked on in graduate school, 2004. I fit a growth model from kindergarten to third grade in this outcome, and I fit a normal distribution for that growth model. Any guesses as to why I might have used a normal distribution for growth in this outcome over time? Vladimir, what's the right answer here? Why did 2004 Lisa use a normal distribution for her growth model of this outcome?
Because I think that she didn't know how to do it properly.
That's correct. I did not know how to do the right version. I had not had any training in generalized linear models. And so I did not understand any of this. I just knew it was skewed, and I was like, well, let's make it work, all right? It's fine, it's fine, it's fine. So I actually did go back to these data, like for my own sanity, and reran what I did, and all of the major conclusions would be the same if I fit the right model. So I'm not going to bag on this publication, but 2004 Lisa did not understand these things. 2000, what is this? 2024 Lisa understands a little bit better. I'm moving towards the knowledge end of the continuum. I'm not there yet, though. We're still working on that. But it makes a good class example. So this is cross-sectional, the last occasion of this study that I'm borrowing here. And that's why the data are not in your download file, because they're real data. So we are predicting proportion correct for an outcome that looks like this. Most of the kids are able to do this. The mean for proportion correct is 0.92. So that number is going to show up in our analyses here. So first step in terms of preparing the data for analyses, there's only going to be two predictors in the story. One of them is a grouping variable for whether or not the child was diagnosed with specific language impairment, which is a condition that is of greatest interest to the PIs on the team. Essentially, it is a condition in which the child has otherwise typical development. They don't have any developmental delays or disabilities, but for whatever reason, they just can't get a hold of grammar. Like, it just doesn't make sense to them. They can't, like, if you ask them if something is grammatical or not, they don't know. And this condition persists across childhood into adulthood, and it's associated with some negative outcomes at that stage. So she's interested in studying this problem and potentially helping children who have it. So whether or not a child has this diagnosis is the main variable. And in every language study studying children's language development, you have to control for mother's education or someone will yell at you. That's just what you have to do. And you might ask, what about father's education or grandma's education or someone else? Shh. No, it's the mom. It's all my fault if my kid doesn't understand grammar. His dad had nothing to do with it. Be that as it may. Those are going to be our two predictors. So those predictors are going to be in the story the whole time. No interactions, nothing complicated on the X side. All of our focus is going to be on the Y side. So in the original data set, I didn't actually have number correct anymore. All I had was the proportion. So I had to reverse engineer number correct, unfortunately. And I did that here. So I generated 100 trials. I generated number correct, rounded to the nearest integer out of the number of trials that were correct times the proportion that I had, or excuse me, the proportion times the number of trials. So that meant like if some child had, 0.88 as their proportion correct, they now get 88 out of 100. And you might be asking, why did you do that? Because the software made me, is the answer. because the binomial model is specified in terms of number correct out of total, not directly in terms of proportion. That's actually a good thing. So I had to create a number correct outcome, and I also had to create a number incorrect outcome to fit certain models that'll be coming later in the example. To do that, I had to find some stuff online. So there's BetaBin or ZBin are some additional Stata routines other people have contributed that I'm going to be using in here. And you can install these, by the way, even if you're using remote desktop. You have access to add-on things like this. And then I made a picture. In R, we are going to be using the VGAM package again. We've used that one before. And I read in the data set in a SAS format, and I did the same transformations here, generated the number of trials as 100, and then built myself a number correct outcome out of the proportion times 100. And made a picture in R2 for good measure. Okay, so first step, always empty model. Why is that always my first step in this class? Am I frozen? Some of you look frozen. I think I'm frozen. There it is. Yep. Pausing. Back to recording. Okay, we're good. We're good to go. Okay, so what was my question? Oh yes, I know. I'm fitting an empty model first. Why am I always doing that first in this class? Anytime I'm dealing with logits in particular. You can talk or you can type. I've got the chat window back open again. Why am I starting with an empty model? Because I thought my handout wasn't long enough and I needed an extra model to start it off? No? Make a comparison? That's a good answer. What's another one? I can tell what the software is doing. That is correct, especially anything involving a logit. And for binomial models, it's even harder to figure out sometimes. So yes, to know what's going on, broadly construed, all correct answers. So I need a log likelihood to make as a point of comparison for any other model that I'm going to try. And I need to make sure I understand what the model is predicting. It could be predicting the number incorrect. It could be predicting the number correct. So we got to figure that part out. So I'm using GLM as the generic generalized linear model routine in Stata. And I had to figure this out in the documentation. Here's link equals logit, family binomial, and then what goes after that is the number of trials that each person could possibly get right. So that variable goes into the model functionally as a denominator for y. So it's asking you what is the outcome you're predicting in terms of number of trials, which is incorrect is what I have here, essentially divided by the number possible in trials. So this is good because this allows you flexibility of addressing different numbers of possible opportunities, right? Like what if somebody didn't get a chance to answer all the questions? We don't want to give them a lower score just because they didn't have enough time. If you have a lower number of possible trials, you can put that in as a variable, and in fact you have to. So everybody has 100 here in this case, but that doesn't necessarily always have to apply. So this gives you flexibility to address unbalance in terms of your measurement of these possible successes. So it's giving me what it thinks the variance function is. That corresponds to straight binomial, where it's essentially the mean is the probability of getting any trial correct times 1 minus that probability times the number of trials. So we have 100 trials in this case. And the link function is the logit of the predicted outcome in terms of predicted number of trials correct, spitting over my words, then divided by the number minus that. So it's putting it into that 0, 1 space essentially. So what I end up with is this number right here, 2.5 roughly, that's in logits. Now we don't know what logits are off the top of my head, but any logit bigger than 0 tells me what about the probability? Yeah, I'll take gestures. What's a logit of 0 correspond to? We'll do a little review. In probability, what is a logit of 0? .5, yeah. So if my logit is greater than 0, I know my probability is greater than 0.5. It's more likely to get any one trial correct on average than to get any one trial incorrect. And if I do my inverse link function, which is right here, e to the logit over 1 plus e to the logit, that gives me a probability of 0.92. So putting it all together, the probability of getting any one trial correct, according to this empty model, on average is 0.92. That is the proportion correct in my data because I had 100 trials. So it's a roundabout way of saying I'm predicting proportion correct. That's what I'm doing in this case. However, this model it does not like. My Pearson chi-square over degrees of freedom is 21. Wah, wah. That means I have 21 times as much variance in the data as what the model is anticipating. That's not good, right? Like to be wrong by a factor of 21 is not ideal. Maybe that's because I don't have my predictors in yet. Okay, let's put them in. Here's what it would look like in R. And by the way, you are not going to have a homework on this unit, just to let you know. I had some difficulty getting the same answers across packages, and I didn't want to make room for this one anyway, but one of the things that I discovered the hard way is that R wants its input differently. The input to a binomial model in R is the number correct and the number incorrect, not the number correct and the total. So Stata wants number correct and total, R wants number correct and number incorrect. 6 of one, half dozen of the other, but the numbers didn't match at first, and that was why. So I've got my -2 log likelihood, so I can use that as a reference point. And here is my predicted probability of any one trial being correct, logits, which is 2.5, which corresponds again to the probability of 0.92 that we had in the data for the proportion correct overall. However, it threw this warning at me. Hawk-Donner effect detected in the following estimates. And I was like, what is that? It sounds like two people's names, but otherwise I don't know what that means. So I had to go digging. And it basically means that the model threw up and it's not really sure if it's 0.92. That's my colloquial explanation. So this tells me that it had some difficulty coming up with this 0.92 estimate, in part because it's so extreme, I think. But here's some more details on what that error message means. However, this model's not going to work. We need to add some stuff to it. So we're going to add some predictors. So what we're doing is modeling the number correct is distributed binomially with the parameter p, the probability of getting any one trial correct, given the number of trials, so that converts to a total number, correct then? So the logit of getting any one trial correct is given by this linear predictor right here. So I have a fixed intercept and two fixed slopes. So I have my NLI versus SLI, meaning not specific language impairment, as the 0 versus specific language impairment. And then I have mother's education measured in years of education centered at 12, so that my reference is a mother with a high school education. Then the mean itself is found as the predicted probability of any one trial correct times the number of trials. And the variance corresponds to what it is under binomial as well. So here's my model. Here, make it nice and big. My constant in logits is 3. Who is that for? What kind of child? What kind of third grader specifically has a logit prediction of 3? This is a review question. Who is this for? My intercept. What's my reference group? Somebody with, yeah, NLI has the 0, so not specific language impairment, and whose mom went to high school, graduated high school. That's my reference kid. That kid has a predicted logit of any one item being correct of 3. It's a lot. Did I figure out what that is? Yeah, I did. That's a probability of 0.956. Pretty high. Now, what happens if you are a child that has a diagnosis of specific language impairment? Minus 1.22. Are they predicted to do better or worse if they have specific language impairment?
Worse.
Worse, yeah, negative, right? So their predicted logit of getting any one answer correct is lower by 1.22. And that is significant according to this model. What if their mom has more education? Are they predicted to do better or worse? Coefficient is positive 0.12. Better, yeah. So kids with more educated mothers have better grammatical understanding. Kids with specific language impairment have worse grammatical understanding, according to this model. Now, do I write it up and turn it in? Probably not yet. What's my distribution fit look like? Oh, 15. Well, I had 21 times as much variance in my data as I should have before. Now it's down to 15 times. So that's heading in the right direction, but still nowhere near write it up and turn it in land. But I've got my minus 2 log likelihood to compare against, so I can test this against other things. In odds ratios, to do that, you need eForm is the command to get odds ratios using GLM. So then it gives you this in here. So note the first one is between 0 and 1 because that corresponds to a negative slope in logits. The second one is above 1 because that corresponds to a positive slope in logits. In R, we can do the same thing and get the, so the model here is C-bind this thing is the outcome. So C-bind number correct and number incorrect is where Y would go. And then squiggle starts what would have been the equal sign. And then here's the linear model that goes after that, intercept, and then the two slopes. Same conclusions in terms of the parameters and the distribution fit, which I had to do myself. So note that I'm doing this somewhat manually, using the residuals function, asking for Pearson ones, summing the squared residuals, and then dividing by degrees of freedom, which is the number for the sample size minus the number of fixed effects. And I can get myself some odds ratios. I did that manually as well. Okay, so let's see if we can do better with overdispersion. So here's one that allows additive overdispersion. This is essentially adding extra variance to the model that's not tied to the mean. It's doing so with what's known as an observation level random effect. So I'm adding that new term in right here. And for those of you who have seen the multi-level class, that will look familiar. That's a random intercept. So it sounds crazy, but I'm fitting a multi-level model essentially to single level data as a way of allowing additional variance. Because in generalized models, when you add random effects, it adds variance, it doesn't distribute it. So this is one way in which you can add additional variance in. To do that, I had to switch to multi-level modeling routines. MEGLM in Stata is mixed effects. Multi-level and mixed effects are synonyms. General linear model. And otherwise the code is the same, but this part right here is specific to adding a random intercept. The variance for it is estimated down here. And we can see if that fits any better. Let me see if I did that. I probably did a likelihood ratio test somewhere. Not yet. Okay, not yet. Here's how I did it in R. I have Glimmer, as I call it, GLMR, which is generalized linear mixed effects modeling. Adding in a random intercept is this little part that does it out here. Here's the extra variability that I added. And here is my index of model fit. It's under 1 because we've added this additional layer of variability that corresponds to each person. So it actually took all of the expected variance and moved it up to there. So that's not ideal. It does look like it fits a lot better though than the standard model. So my likelihood ratio test is 900, which for 1 degree of freedom should be pretty darn good. Here's an alternative version that has multiplicative overdispersion instead. And note that I tried my best to notate it, but I'm not sure this is right. The reason is because I read about 4 different things to come up with this, and they all notated it differently. So this is as close as I can get as a reasonable 2024 Lisa, okay? So maybe in 20 years, I'll be like, hey, I finally figured out how to do this. And then 2048 Vladimir can tell me about, how that Lisa didn't know anything. I don't know if I'm still going to be doing this in 2048. I'll have to think about that. At that point, I'll be ready for retirement and I'll have to decide if I'm still in it or whether I'm just ready to go live on a boat somewhere or something. But I don't make boat kind of money, unfortunately, so I'm probably still going to be in it. Anywho, this is the one that I think is going to be more useful as a general thing. To do it, though, I had to find it. And so there was something called BetaBin in Stata that is a user-defined package that will do this for you. And it fits specifically this beta binomial model. So the general idea to this is that it takes binomial in which the variance is a function of the mean, and it adds additional variance to it as a function of the mean. So it allows for that additional skewness that we see in the observed data that's beyond what the binomial would anticipate. So it's multiplicative over dispersion in this case. So this is where we get into what is it giving me? Different versions of the scale factor, either log over 1 over that or 1 over that of what it was in SAS. It doesn't tell you what the Pearson chi-square over degrees of freedom is. Unfortunately, you'd have to be able to figure that out. I went to R to do that instead. I was able to develop a measure of effect size for the model overall, though, by correlating the predicted number corrects with the actual ones, so the proportion corrects, and it looks like this model accounts for about 16% of the variance, so not too shabby. In R, I did the Pearson chi-square fit, and I came up with a value of 1.8, which is much, much better. So we're closing in on something that looks like it would be useful with that one. All right, but we're also closing in on 315, and therefore it would be useful for me to shut up. How's that sound? Maybe I could put that more nicely. It is time for me to conclude the class session and ask if there are any further questions or comments at this time. Okay, so
Lisa,
yeah, hit me.
sorry, but I have a quick question now.
Sure.
That you showed us the first and the second model, the empty model and the model with some predictors in it. The thing is that in the first model, we saw that the Pearson chi-square number was something like 21, but after including predictors, that number was reduced up to 15.
Right.
So the question is, in the other models that we have seen, we have seen that Pearson thing, that fit measure is important. And we have been changing conditional distributions to see what the effect of those new conditional distributions was on that number.
Yes.
But now that we saw that including predictors can also help us to reduce that number, the question is, when we are trying to get our final model, what's more important? adding predictors to reduce the number, or trying to use different conditional distributions? What's better,
Yes.
or what do you think about it?
The answer is yes. Do both.
Yeah, because the question now is hard.
Yeah, I mean, the predictors, like, they can explain why it is that some of those cases that were in the skewness are there, right? These are the kids that have a disability. And so, to the extent that that's explained, what's left over might be more binomial like than what was there to begin with.
Exactly, yes.
So, once you're out of predictors, right, like you can't add anything else, then you can refine the conditional distribution to what's left over at that point.
Yeah, yes. Thank you, Lisa.
Thanks for the question. Other questions or comments? Okay, then your next task is the homework 5 outline, please. On Monday, I'd like to see those, and we'll talk about, we won't talk about them on Tuesday, but we'll talk about this stuff on Tuesday. How's that sound? All right, then, have good weekends. Let us know if you need anything. Bye for now, and thanks for being here.
Thanks, Lisa.
Thank you.